Hi, this is Professor Snell. Now, speaking to Environmental Systems 2. A number of people told me that the video I did for the last assignment was helpful, so I thought I'd make another one. Let me make a general comment, though, about this. Let's just remind ourselves what's going on in this class. We're covering a huge amount of area, and so it may seem like it's complicated and there's too much going on, and maybe it gets confusing. But if you look at how I'm grading and what I really say that I'm expecting is I really just want you to understand some basic concepts here. And, it's crazy. We have a class that's 3 hours long where we're covering energy, right? The whole huge topic of energy. We're talking about alternatives and how, giving some context for how most of it's solar, and there's, wind and hydro versions of solar, and talk a little bit about climate change. And then so we mentioned photovoltaics briefly, a couple slides about it, and say, this is sort of a central way that it's done, and I talked about a couple projects, but there's no way, you don't know much about solar electric coming out of that, and so we're never going to ask you for some complex understanding or calculations. So really, typically, if you look at these assignments and just sort of step back and say, what's really being asked here, it's going to be pretty straightforward. I'm not saying it's easy or that you don't need to ask me questions. You definitely do, and you should. But just look at the assignment always and think, okay, what's really going on here? Reminding myself that it's going to be pretty straightforward. So this one, the goal is to calculate a daily average energy usage from lighting and plug loads, determine an appropriate number scale of solar panels or other photovoltaic PV system to meet the load and locate the system on the building appropriately. Okay. We're going to put this on the roof, first of all. That's what's going to be appropriate. So let's just start with that. That's the place that gets the most sun. It's elevated, so it's going to be the least shaded. And we don't want any shading on our PV, right? So we're putting it on the roof. Then what's this first thing? Daily average energy use for lighting and plug loads. Ooh, that sounds scary, but wait a minute. Lighting, we just did lighting, so we know what lights we've got, and we know how much power they use. So we just got to figure out how much they use per day, and then turn that into how much power per year, because we're designing a system, or sizing a system that's going to produce that power, or some of that power. And then plug loads, we talked about briefly. That's just what you plug into a wall. So in the case of a gym, we might have treadmills. There's a printer in the office, which you can pretty much ignore because it's going to be such a small amount. And if we wanted to get into equipment like the heat pump, then that would be a much larger load. And so you could do that. And the assignment right here is just saying lighting and plug loads. If you want to keep it to that, that's fine. And then all we're doing is saying, okay, how big does the system need to be? And big means how many square feet does it need to cover on my roof in order to produce whatever amount of power I have decided I want to produce. So let's just talk about how to do that. Okay. We have our gym project. And maybe it has some other component to it, whatever the geometry is. It's however many stories. Whatever. What we're saying is that we're gonna put a photovoltaic system on the roof, and we need to know how big it is. So here's our PV system. And the question is, so we're sizing a PV system for our project. First, let's just remind ourselves what PV is. There's a couple slides that I showed quickly that basically said, okay, we have this thing called a PV cell, or solar electric cell, solar cell. It's got, a semiconductor up here, a different type of semiconductor down here. When the sun hits it, that induces electricity or electrons to go through this center section, and electricity comes out. This is called a solar cell. If we put a bunch of these together, that's called a panel, and a number of panels together is called an array. And there's more to it. You know, these are connected to a charge controller and can go to an inverter so that we can produce AC power. There can be batteries in the grid. But we're not really concerned about that. Right now, we're just talking about how big is this system? How many square feet? So that's the first thing, is that we're talking about square feet. That's what we're outputting here. That's the whole final deliverable, essentially. I mean, there's, you have to give your calculations and everything, but that's what we're looking for. So how do we get to square feet of solar electric system? Well, first we're talking about power, right? How much power? And remember, that's in watts. We just need to review that. So, because, power was volts times amps, which equals watts. We know that, light bulbs, 100-watt light bulb, we're used to hearing that. So first of all, we need to figure out how much power we need. And that's going to be our loads. And we're not talking about the entire loads of the building, most likely. Might just be lighting and plug loads. So we were saying at a minimum, we're talking about lights and what's plugged in to outlets. But maybe we would also decide to look into our equipment, like heat pump or whatever. So light, plug, equipment. And our units are going to be watts, but actually kilowatts, because we're going to have a lot of watts, so thousands of watts. But that's just the amount of power that's being used by all this equipment. We need to know how long it's being used in order to figure out how much power we need to produce. So we need it per hour, or how many hours, not per hour. We need to have how many kilowatt hours, because a kilowatt hour is a kilowatt being used for an hour. And that's per year, because we want to figure out the entire year's usage, just because that system's supposed to be producing for the entire year. So kilowatt hours per year is our next output. And so then we need to figure out how much our roof can produce in our climate with any obstructions we've got, etc. And that's also going to be then in kilowatt hours per year, but we need it in per square feet, because because that's what we're looking for, is square feet, right? And remember, the idea then is that if we have the sun beating down on our roof over here, we want to know how much energy is hitting a single square foot, so that we can then say, well, how many of these square feet do I need in photovoltaic panels to produce the load that we require? So then, and this is a basic thing you should always do when you're talking about equations like this, and especially simple ones. We're saying, okay, we need to get from kilowatt hours to kilowatt hour. We need to relate kilowatt hours and kilowatt hours per square foot per year to get square feet. Well, that means we're going to need to say load divided by production per square foot. And so that's going to simply be kilowatt hours per year divided by kilowatt hours per square foot per year. If we rearrange this, right, we're going to flip these around, because to take this up to the numerator, it's going to be kilowatt hours. Well, let's do it again to make it really clear. Kilowatt hours per year is the load times square foot years over kilowatt hours, right? All we did was just flip this around to bring it to the numerator, and now everything cancels out. Kilowatt hours, years, and we have square feet. So this is what once we get our load and our how much we're producing per square foot per year, we can generate our square feet. All right, so let's figure out our loads. How are we going to do that? Well, we have a thing that's producing, or that's, I'm sorry, that's requires power. Make sure this thing's still going. Yeah. I just did this and it didn't work. I mean, that, like, my equipment crapped out in the middle of it, so I'm just trying to make sure I don't do it again. Okay, so we have a thing. It's using a certain amount of power, so a certain amount of kilowatts. We have a certain number of those things, right? So if there's multiples of them, we need to know how many we have. We need to know how many hours per day we're going to use it, how many days per year, and that's because we want kilowatt hours per year, which is what, if we have all of these variables in a row, multiply them together, we will get kilowatt hours per year. So our thing is, for example, we'll have a light, and we already know what lights we're using because we did that in the last assignment. How many lights and how much power they're using. So I'm going to make this easy. I'm going to say that our light number one uses 1 kilowatt hour. Uses 1 kilowatt. That's its draw. That's what it's rated for. We're going to have 10 of them. They're going to use 10 hours per day of energy, where they're going to run for 10 hours a day, and they're going to run 100 days a year. So that's 100 times 100, 10,000 kilowatt hours per year. And then we're going to have other lights, right? So we're going to have a light section. And, 1, 2, 3, 4, whatever. And, those will add up in this row. Then we're going to have some plug loads. And that'll be a section of those. So we might have, like I've already mentioned, a treadmill. And let's say we have, I looked it up. I think I don't know. One side I saw between 300 and 700, I think, watts. I'm going to say we've got 500 watts, so it's going to be 0.5 kilowatts. I'm going to say that we have 4 of them. And just to be simple, they're also running 10 hours a day and 100 days a year. So that would be 2,000 kilowatt hours per year. And then we'll have some more plug load stuff, whatever that is, and add those up. And then we might do equipment. We might think of other things that we want to put in here. And again, this is not the requirement for the assignment, was just lights and plug loads. You can stop there, but you can go further if you want to, if you're curious about how much you would actually need. And also, as you move forward, these classes are additive. You're going to want to be able to quickly do these kind of calculations, I would think. So you could take it as far as you want to. But let's say, so we've got some, other, some other amount here. And let's just make up that if we sum all these up, the total is going to be 100,000 kilowatt hours per year. And this is then our load. And you can kind of already imagine, and I showed this in class, this could be in Excel. And so this could be a cell in Excel right here, right? Then the next thing we need is our production per square foot. And that could also be in Excel, obviously. So how do we do that? How do we calculate that? So let's remind ourselves again what's going on here. We've got the sun, and we're in a specific climate on a specific site with specific obstructions, etc. We want to know how much energy that sunlight at our site is depositing per year on a square foot of our roof. So 1 foot by 1 foot. So how do we do that? I'm going to go open up Climate Studio. I'm doing this for Phoenix right now. I'll show you also New York, but I don't want to do the exact same thing that you're doing. It seems a little silly. And my point here is that, by the way, we can do this. You can do this on your. Let me start here. Here is that building I've used for a couple of things in other assignments or examples in class. It's an office building. I have it. Here's a radiation map in New York. And let me remind you how this works. I showed this in class. We've done these before, so you should be getting good at these. But so first of all, I have to define my climate. I bring that in here. It's a straightforward thing to do. Then I choose radiation map. Radiation map is all you need to run a radiation map is you need to, anything that you want the sun to be hitting and measuring how much sun hits it, you need to have those those surfaces defined. Materials defined for those surfaces. So I'm just gonna do the ground and the roof on this one right now because that's really all I'm curious about. So I've only got these two materials chosen. I click on it. I can choose materials that already exist. Then I have to come in and say I want. And actually, I decided only to do the roof here. I didn't think the ground would have much effect on it. And so I just selected my roof, which was a surface on a layer. Oops, sorry. And I then said, make a surface out of it, which you just, by clicking this little icon. So I'm now ready to run my simulation. I've got materials on the roof and the ground, and I've got a surface that I'm going to be measuring, which is the roof. I hit go, and I get a simulation like this. And we'll see here that I've got 1,440 or so watts. These are kilowatt hours per meter squared per year, 1,430. You don't have to do it actually on a building. And the reason I'm showing you this is because to show you that this is the sun. And so if I'm defining it for a site, it's going to be the same. So if I come over here to, that was New York City. If I'm here in New York City, got basically the same amount here, 1440, which is about what we had before, kilowatt hours per meter squared per year. All right. And that's the amount of sun hitting the roof per square foot, well, in this case, per square meter per year. I'm going to switch to Phoenix. The first point is to see, look, there's a big difference. You see here 1430, like we were saying, or 40 for New York City. For Phoenix, it's a lot more as we'd expect, 2045. kilowatt hours per meter squared per year on this roof surface. So it's important that you choose, the correct, wherever you're located. And also, if I were to add context to this, so for example, this big tall building, so if I were actually on a site that had some kind of obstructions or context, now I'm talking about a much lower amount here, right? Because I'm getting a lot of shading, and it actually changes between the front and back of the roof. So if I had PV in this situation, I might want to focus it back here at the back because I'm getting more sun there. So this is why it's good at this stage, the schematic design stage, to always use something like Climate Studio, because then we're actually dealing with our actual site rather than going and looking up some PV panels, seeing how much they make, maybe then generically figuring out how much energy is coming to the site without a model. Anyway, this is a better way of doing it, in my opinion. So that's why I'm doing it this way. There's other ways of doing it, and I think that maybe Professor Thomas's class is doing it coming from a different direction. So that's why I think it's important to try to think these things through and do it in a way that makes sense to you. So you don't have to do it this way if you don't want to. Anyway, so we were talking about, so now here the idea is that we just simply have to figure out what are we trying to get to. If we go back to our, remember we're trying to get to kilowatt hours per square foot per year, right? So if I come back to my, where am I now? Well, I'm at kilowatt hours per meter squared per year for this roof. Well, I'm pretty close. I just got to convert that to square feet, and I'll have my answer. Pretty simple. So how do I do that? I think since I already did this. Yeah, I just typed in meter squared to foot squared in a browser to get my conversion unit if I don't remember it, and it's 1 meter squared is 10.75 square feet. So all I have to do then is come back here and say, okay, I was at 2045 kilowatt hours per meter squared per year. So if I say 2045 divided by 10.75, get about 190 kilowatt hours per square foot per year. So I'm going to come back and just, so we're saying that for Phoenix, I'm getting a huge lag here now, so I'm going to probably go set some stuff down here in a second. For Phoenix, we have 190, and I'm going to call this solar energy. We have 100 solar energy equals 190 kilowatt hours per square foot per year. Now, let's just go check our, let's check this, because there's another way we could, and this is not a bad thing to do, just to make sure that you're, haven't made a mistake. If I go back to my, there's other ways of doing this, just the way I typically do it, and I switch it to IP, which audio is on, that's interesting. See, now I'm at kilobtus per square foot. So kilobtus per square foot per year, 650, we'll say. So how would I convert that? Well, I just typed in BTUs to kilowatt hours, and so we're at 650 kilobtus, right? That's what we're at over here. 648, 650 kilobtus. So this is going to be 650,000 BTUs. That's a kilobtu, right? 650 kilobtus is 650,000 BTUs. And we get 190 kilowatt hours. And so if we look back at our, I'm sorry, here, it's the exact same amount. So we're pretty confident that this is accurate. Phoenix without obstructions. Now, the issue with that is, though, that remember that we talked about briefly in the lecture that this PV panel being hit by the sun does not produce, it's not 100% efficient. And actually, we've been saying, you can look it up and do different amounts, but we were saying the PV efficiency rate was about 0.2, so 20%. Actually, let's say PV efficiency. Man, it's so hard to write when you can't see it. So there's like a half-second lag here right now, but I'm trying to soldier through. Okay, so in order to figure out how much light is actually hitting this PV panel, we have to multiply that 190 times 0.2, and that is, actually, let's come over here to our fake Excel sheet, and yeah, this lag is driving me crazy. I think, am I done with? Yeah, I'm gonna close down. I think we've done what we need to with these, so I'm gonna close these down. See if that gives me a little more bandwidth here. And I don't think I need this anymore. Okay. So we had our load. Then we were saying we have our solar energy, is what I was calling it. You can call it whatever you want. Just to get a name for it. We said it was 190. That's also kilowatt hours. That's kilowatt hours per square foot per year. And then we have PV efficiency. We said that I'm putting in 0.2. You could put in something different, or you can use 0.2, it's fine. Then so PV per square foot is going to be this 190 times 0.2. 190 times 0.2 gives us 38. So I'm going to say it's 40 kilowatt hours per square foot per year. And now we have our two values that we needed over here. We said we've got, so this is our load and this is our production per square foot. So if we divide these two, we will get, I'm going to say array size. This is going to be in square feet because kilowatt hours per square foot per year. If you take kilowatt hours per year and divide it by kilowatt hours per square foot per year, we're going to get square feet. And so 190 not 190, sorry, 100,000, because that's our total load, divided by 40 is 2,500. So our array size is 2,500 square feet. So this is our main output. Yeah, I've been getting larger and larger as I go. This is this, right? Okay, so we've got our answer, 2,500 square feet. Is that realistic? I mean, realistic, that's not what I mean. Could we actually put that on our roof? So let's say our gym or this building could be 100, I don't remember how big y'all's buildings were, 150 by 30 would be 4,500 square feet. And we're talking about, let's just come back here and do our total answer. So we're saying the load was 100,000. The P per square foot was 40, and so then the square foot was 2,500, 2,500. And our roof, if it's 150 by 30, would be 4,500. So that definitely could fit on there. You know, I don't know, maybe you're at 100 feet. That's still 3,000, could still fit on there. And if it couldn't fit on, then we could say, well, we're only going to use a certain, we're only going to supply a certain percentage of this load that I completely made up out of nowhere, so I don't really know what it would really be. Or we could, you know, we could put some down here, and we could put some out here on the ground if we had space. You know, that could be up on some kind of you know, mount, so that it could even be articulated. So, you know, we could change its angle during the year, whatever. So that's basically the way you would do this. It took me a while to tell it to you, but I think now that you see it, it's shouldn't be that difficult. Of course, if you have any questions, let me know. I think I may make another video that's talking about the whole PV watts thing, which I just mentioned in class because I was saying there's other ways of doing this, and just wanted you to go, oh, PV watts, maybe I'll check that out sometime. But I'll probably look at it in a video and show you that too. It's optional. All right, hope this helped.